In this collection of videos, we are going to talk about some drawbacks to the naive nearest neighbor methods that we've studied so far, and we're going to talk about ways in which we can make improvements to those methods. So just as a bit of a review, last week we looked at collecting a bunch of text input, and we were working with examples of movie plots, and we were comparing different movie plots for similarities between the movies. And so the question more generally was, given a text input, can we determine other texts in a large collection of documents or corpus that are somehow close to the given text document? And we looked at both Euclidean distance and cosine similarity. And the method that we were using, where we would take a query point or a particular given text input and search via some type of distance metric for something that was the most similar to that, and return that most similar text document, is called a nearest neighbor method. And more generally, you could talk about the k nearest neighbor method if instead of recommending the 1 nearest neighbor, we wanted to recommend maybe 5 nearest neighbors or k nearest neighbors. That's the type of model that we're employing right now. And there were benefits to this. For example, the standard story with data science is to introduce a method and introduce whatever distance metric we're using, and then talk about the type of error that that's going to produce. And we often have this training set and this test set. Here, we are searching through every possible document of importance, and we are computing every single distance method. And so there was no discussion of a training set and a test set and what is the error that's going on here, because there isn't any error. We've searched through everything and we've found the smallest thing. So the only extent to which we discussed error was what are the drawbacks of the distance metric that we're using. That's where that discussion really happened. However, because of the fact that we might have a huge data set and we're converting text documents and we're looking at all of the words in all possible documents, we start getting these absolutely huge collections of data that we need to sift through. And so there's a huge computational expense to making every single possible distance computation, no matter what the distance metric is. And so we experienced large wait times, we experienced memory issues, and if we were to go from nearest neighbors to k nearest neighbors, or if we were to get a larger data set, which happens more and more in data science, the drawbacks of this method start to be that we run out of time and memory, as opposed to we have a model that doesn't quite capture what we want. So the question becomes, how do we speed things up? And we're going to look at 4 different ways that we could speed things up. First of all is we should use what are called sparse matrices that are built into Python. We were working with arrays, which are generally very slow, so that we could use our own functions that we created from scratch. Almost always in Python, that is not the answer. The answer is to employ the methods that Python already has built in the library. Those are going to be much faster. Recall that Python is a language that has its own internal way of wanting to do things. And if you ever try to fight that, Python will work with you, but Python will not work well with you. And that's what we were seeing last week in our Jupyter notebook. That's a Python specific thing. However, we are going to talk about more general algorithmic things we could also do, such as tree pruning, that we're going to talk about KD trees and how we can use these to not compute quite as many distances, regardless of the distance metric that we're using. But another thing we're going to get to that'll get us back into the realm of more data science methods is that most of the time when we're doing a recommender-based system, like what to watch next on Netflix, or what we might enjoy on Hulu, or what songs we might like if we enjoy this song, any kind of recommender model doesn't really need to be perfect. It needs to get me something that's good, but it doesn't necessarily need to be the best. And so if we can switch our focus from finding the exact nearest neighbor to just finding a neighbor that's pretty close, even if it's not exactly the best or closest neighbor, that's going to really help us find some more computational savings. And so using a combination of all 3 of these things, knowing the programming language you're in and using it most efficiently, pruning your sample space so that you're not searching through every possible document, and then employing methods to just find something that's a pretty good approximation without being perfect, a combination of those three things can really get us into a space where we can make product recommendations instantly, which is what our applications are going to really require, like Netflix or Hulu or Amazon. So let's just go through a quick visual of the idea behind KD trees, which is the first thing we'll be taking a look at. The idea is, let's split up our data into these bins. And I think of bins as sort of the leftmost picture and trees as the rightmost picture. So let's take our data and let's break it approximately in half and say, I have a bin over here and a bin over here. And let's continue splitting our data into these smaller, more manageable chunks. So let's split each data set again, perhaps in half somehow, then again and again, until we're satisfied and we have a reasonable number of data points inside each bin. At that point, if we're keeping track of bins on the left and trees on the right, we can very easily attribute to the tree a numbering system where the left branch corresponds to a 0 and a right branch corresponds to a 1. And we can come up with these identification numbers for each bin that represents the path you walked on the tree to get there. I went left and I went down, and then I went left and I went down again, gets me over here, etc. And so we have these bins over here, and we have a corresponding path that we walked to reach that bin on the tree on the right, a series of choices we made in order to reach that particular bin. Then the way that our KD tree method is going to work is we're going to identify a query point. And instead of just searching through the whole collection of data points one by one and computing distances and finding the smallest, we're going to start our search in the bin that contains the query point by computing the distances between these, in this example, 2 other data points. What we're going to then do is, of the ones in our bin, we're going to identify the smallest, and we're going to create a little radius around our query point and that nearest neighbor so far, and say, I really only care about data points that will put me within this circle. Those are the only data points that could possibly be my nearest neighbor. Now, what will happen in practice then is we will identify bins that overlap with this circle, and we will say, if I am a bin that overlaps with this circle, then I will compute the distance between my query point and every point in this overlapping bin. From there, I'll identify the closest neighbor and see if any of those is smaller than my nearest neighbor so far. And if so, I'll put a little bubble around my query point of this new nearest neighbor's distance, and I will search bins that overlap with that particular radius. Now, it happens to be the case that if I move on to the next bin, so to speak, and look at it here, this bin lies outside my circle, and so I don't want to consider it. And in fact, for this picture, all of the bins lie outside that circle or have been searched so far, and so I'll never compute the distances to any of the data points that live in any of these other bins. I'll only have computed distances between the points that are in the original bin and then inside the bin that overlapped with that original circle, and I'm done, having done significantly fewer computations than checking every document in the corpus.